Calculating DC motor values. What we're going to focus on in this presentation is armature values and calculating torque, because those are the ones that typically pose the most challenge for students and don't seem to make a ton of sense when we're looking at the numbers we're getting. So let's take a look at the basic operation of a typical motor. And I can't stress this enough that really any motor will operate in the fashion that I've outlined here. Any motor, anywhere. We just happen to be talking about DC motors. So here's a DC motor. It's connected to a DC source. And then on the shaft, we've got this highly accurate and detailed diagram of a conveyor belt with boxes of frozen chicken being transported. Now this is showing a relative small mechanical load on the motor shaft. Remember, the motor shaft is where the mechanical power is coming from, and that would be in torque, right? Rotational force. So if there's a small mechanical load on this, small mechanical load, let's think of it as small amount of mechanical power required, that would then require a small amount of electrical power. When we start to increase the mechanical load on our motor, we see that as the mechanical power requirement increases, the electrical power increases. And so if the voltage of the system remains the same or consistent or unchanging, that would then mean that the current value would have to increase. And so this statement that I have at the bottom is really valid for any motor anywhere. As mechanical load is increased, it causes a reciprocal or a reflected requirement of watts in the motor to match it. And that then causes an increase in the motor amps. So a motor is a very unique electrical device. Although it has a rating, and the rating may simply be 100 amps and 10 horsepower, we won't see the 100 amps on the line conductors unless the power that's required to drive the load is equivalent to 10 horsepower. So if I have less than 10 horsepower that's being driven by the motor will draw less current. If I have more than 10 horsepower, then the motor will draw more than its rated current, so over 100 amps. And so it really is dependent on how the motor is being used in the circuit. Depending on how the motor is used within its lifespan can determine how long it lasts, because if I'm regularly underloading it, that means less current, less heat. It's probably going to last longer than something like this, where there's a ton of mechanical load and a ton of electrical current and a lot of heat. So let's take this information then and calculate some armature values that help to prove why in a DC motor specifically does the current increase, other than just the basic logic that we've looked at here, which is power output and power input are relatable values. So first thing we want to look at is just the basics of motor action. And motor action, we know, is composed of a conductor that has an external source that's connected to it, which causes a current flow. If I wanted to determine the direction of the magnetic flux around this conductor, I would have to use my left hand. And the left hand I'm using to determine that direction of magnetic flux. The thumb points in the direction of the current flow. The fingers point in the direction of the magnetic flux. And so thumb has to point into the page like that. And then really what we're doing is we're wrapping our fingers around it like this. And so what that means is that the magnetic flux is traveling in this direction. It's traveling in that direction. Now, what happens when I place this energized conductor into a magnetic field is there is now going to be an interaction, right? And that interaction is between all of these magnetic flux lines that are all traveling north to south. And what will happen is, due to the EMF, or the electrical energy that is in this conductor causing these lines of flux, it will move the conductor. And the movement of that conductor is going to be according to the right-hand rule. Right-hand rule. Thumb indicates the direction of thrust, so we're not sure which way it's going to be forced. Index finger points towards the south, and the middle finger points towards the direction of current flow. So what that means, right-hand rule, is that the conductor will be forced in an upward direction. Conductor will be moved this way. Well, that's all fine and great. It's going to move, and obviously a single motor will not use an individual conductor, but through the right-hand rule, we can see that the motor conductor here will be forced in a vertical direction up, not down. But wait, there's more. As that is getting moved up, isn't it breaking lines of flux? It's breaking those lines of flux that are traveling from the north to the south. So something bizarre happens here. As it moves, so I'll draw it again. There's my conductor. There, this would be the main source EMF. But as it's being moved, it's breaking lines of flux. And we know that if it's breaking lines of flux, we've got Faraday's law of induction and Fleming's left-hand rule. Oh, there's a left hand. We could then determine another value of voltage. Bizarre, right? So my thumb would indicate the direction, relative direction of cut. My index finger points towards the south pole. Middle finger would actually be pointing out of the page or out of the screen towards you. Well, that's bizarre. What that would mean is that we would have yet another value of current that would be induced. I'm going to use red. That would be induced into this conductor. And what's going to end up happening is we are going to get lines of flux traveling in the opposite direction. And what these are referred to as are counter EMF, much the same as what we've looked at with inductors and coils and inductive interactions in DC. So counter EMF is going to be set up. Now that counter EMF is going to oppose the main source EMF, and that is also going to oppose the main source current. So let's take a look at some of the calculation that we can use with this information to validate the current increasing or decreasing on a motor. All right, so we have our conductor here. It has some main source EMF, right? Main. And then we have our counter EMF going in the opposite direction. And it will cause a current to flow in the opposite direction, counter EMF. And what we can then sort of look at this as is the magnetic flux density is really Webers, okay? So mag flux density is measured in Webers. And if it's measured in Webers, what that really means is that the main and the counter being in opposition to one another, if we said we had 15 Webers worth of magnetic flux that was traveling in one direction, and we'll say that's the main, and then we had 5 Webers of magnetic flux traveling in the other direction, and we'll call that our counter EMF, then what we're left with is less, right? Less Webers worth of magnetic flux, and we would call that the end result, and we would also refer to it as the effective value of EMF. Because they cancel each other out, there is an effective value that's left over. And that effective value is something that we're going to use in our calculations. So another way to visualize this is by looking at the conductor inside the motor, where we have, there's the conductor, and the conductor has current flowing on it, which is from the applied, which is the main source, and it's a significant value of current and EMF, right? And then we're going to take that applied value and we're going to have to subtract the counter EMF because it's in opposition, isn't it? And it's a much smaller value, so it's not as significant, right? And what that will give us is the E effective. And the effective is going to be this subtracted from there, or this one having the counter EMF subtracted from it. So it's going to be slightly smaller, right? So I of the armature is equal to E effective divided by the R of the armature. Oh, E effective, there. R of the armature. So if we know what the effective voltage is here, and we know what the resistance is of the armature, it's Ohm's law, then I can work out the current through the actual armature. So this means that as we go through our different situations of no load and full load, we can draw some conclusions. So no load. When the motor's at no load, or let's say very little load, the rotor will spin fast. It's always going to be spinning a little bit faster than what its rating is. Now, it depends on what type of motor we're referring to and how much faster, but it's always going to spin a little bit faster if there is no mechanical load on it. That means that there is lots of flux being cut by that conductor because it's turning so quick. It's cutting lots of lines of flux between those two magnets. And if it's cutting lots of flux at a really fast rate, that means there's going to be lots of counter EMF. And if there's lots of counter EMF, there's counter EMF. E applied minus counter EMF equals E effective. That means the E effective will be rather low. And if the effective value of voltage is low, take a look at Ohm's law. Does the resistance of the armature change? No, of course not. It doesn't change. That means the I of the armature would also be low. And that kind of makes sense, doesn't it? Because at no mechanical load, the motor isn't really working very hard. The motor is working very lightly and doing almost nothing. When the motor is at full load, and again, full mechanical load, the rotor will spin slower. And if it spins slower, then that means that there is going to be less lines of flux being cut. And if there's less lines of flux being cut, that means there's going to be less counter EMF. And if there's less counter EMF, look at this, less counter EMF, this gets smaller, then what happens? The effective voltage would be higher. So E effective would end up being high. And if the effective voltage is high, look at Ohm's law, E effective divided by the armature resistance would equal a higher armature current. I of the armature would end up being high also. And that kind of makes sense, doesn't it? Because when it's fully loaded, you want to see, or you would expect, higher current because it's requiring more electrical energy in order to fulfill that mechanical loads requirement. So how do we actually use this then in calculating a value? So let's take a look at some of the numeric values involved in this. Let's calculate a DC motor. And the first one we're going to calculate is just a series motor. So here's my series motor. I've got 200 volts DC. I've got 15 amps. And I've got a series winding here and an armature. The armature has a resistance of 1.1 ohms. And we know that the actual series winding typically has a fairly low ohmic value as well. So I'm going to say the voltage across that series winding is 20 volts. So the question becomes, why is this motor only drawing 15 amps? Like, why is that? Why is the motor only drawing 15 amps? Because, I mean, if we use a little bit of Kirchhoff's voltage law, we can see with this, the armature value here of 1.1, that if there's 20 volts here, there has to be 180 there. And if there's 180 there, then wouldn't this then kind of take precedence? Like I is equal to E over Z and E is 180 and Z is 1.1. Wouldn't that make 163.6 amps? And the answer is, well, no, because there is more to the story than simply volts and ohms, right? What's adding to this story and what leads to confusion is the fact that I of the armature, I'm going to put in brackets here, armature is equal to E effective divided by R of the armature. Remember, effective voltage. Is this the effective voltage? No, this is not the effective voltage. Rather, it is the voltage drop across the armature. We need to know this. And the key to this, there's a few different ways that it can be sketched. So let's take a look at one of the other ways that we can show this information. IA is equal to E effective over the resistance of the armature. And another way that we can use this, E effective is equal to, keep missing that second F, EA, so remember, every time I write A, it's armature, minus EG. And EG is counter EMF. Now, the way that you'll find some texts describe this relationship is with this equation here, but most people don't find this to be as good a portrayal of what's happening within the armature. Okay, so this here, although true, I find most people align a little bit better with what I presented on the left. So if we go back to our motor had this value, right? It was 1.1 ohms. It had 20 volts, 180 volts, 15 amps, and then finally just 200 volt source. So let's work out these values. We're going to solve for E effective of this motor and EG of the motor. Okay, E effective and EG. So first thing, E effective is equal to IA times RA. Right? What did we do here? IA and RA. So what we did is we took this equation and we just manipulated it. This is Ohm's law, isn't it? It's Ohm's law. So IA and RA, we know the current already. It's 15 amps, and we know the resistance, 1.1. So what we're going to do is multiply the two. 15 amps times 1.1 ohm. And that gives me an effective value of voltage of 16.5 volts. I'm then going to solve for EG, which is the counter EMF. And EG is EA minus E effective. So we are using this formula here, but again, we've manipulated it in order to solve for the missing variable. EA is 180 volts. That's the voltage across the armature. That's a measurable voltage, EA, minus E effective that we just calculated, 16.5. That means the total counter EMF is 163.5 volts. Given this information, would we say this motor is heavily or lightly loaded? And the way that we could determine that or make a conclusion about that is looking at the effective versus the counter EMF. The counter EMF is, we could say it's quite large. It's quite large. And because of that, if the counter EMF is large, that would mean that the loading of the motor is quite low. So we'd say this motor is not heavily loaded. Let's look at another calculation with these values. This one is going to be with a 200 volt source, DC, and we've got our armature. I'm going to keep it at 1.1. And this time we are going to have a shunt winding. And the shunt winding has 100 ohms worth of resistance. And the total draw of this motor on the source is 36 amps. We are going to calculate E effective and E counter EG or counter EMF. So solve for E effective and EG, which is our counter EMF. So first thing, let's write out our two equations that we're going to use to solve this. That would be E effective is equal to IA times RA. And EG is equal to EA minus E effective. All right, so I need to know the armature current and the resistance. I already know what the resistance is, 1.1. How much current is actually flowing here? And in order to answer that, we need to know how much current is flowing in the shunt winding. Well, the current in the shunt winding would be dictated by the voltage across the shunt winding and the resistance of the shunt winding. So 200 and 100 ohms. Using Ohm's law, 200 divided by 100 would give me 2 amps. 36 and 2. So we look at the junction, 36 enters, 2 leaves, which means another 34, or the remaining current, continues on through the armature. So now we have enough information. 34 amps times 1.1 ohms gives me a value of 37.4 volts. That's the effective value of voltage. Over here, the counter EMF, that would be our EA. What is the voltage across our armature? There's no other object here. And what that means is that the voltage from these 2 points is the same as the voltage from these 2 points and the voltage from these 2 points, which means 200 minus effective 37.4 gives me a counter EMF of 162.6 volts. Let's do one more. It's going to be the same size of motor with the same source, 1.1, with a 100 ohm shunt winding, but this time the current drawn by the motor is substantially higher, 150 amps. Again, let's solve for E effective and E counter EMF, or EG. So E effective is going to be equal to IA times RA. IA, so 200 and 100. Has the current changed through this winding? And the answer would be no. 200 volts, 100 ohms equals 2 amps. If there's 2 amps, it means 150 minus 2, the remaining 148 amps must be flowing through the armature. 148 times 1.1. 148 times 1.1. What does that give us for a value? We get a total of 162.8 volts. Over here on the EG side, EG is our E across the armature, and EG is the getting all screwed up now, EA minus E effective. There we go. EA is the voltage across the armature. That would be 200 volts minus the effective 162.8. So 200 minus 162.8 gives me 37.2 volts. So in comparison, we could say this motor is more heavily loaded. Mechanically, there is a significant mechanical load on this. And we can tell that because, well, obviously there's a significant amount of current here, but to prove that, the effective value is high and the counter EMF is low. Let's take a look at calculating some torque values. Torque in any motor can be calculated with this formula. Torque is equal to K flux I. K is a constant value that's given. It's an engineered constant. Flux would be the Webers of flux. And finally, I is the in-phase armature current. Now, not really that important to say in phase with a DC motor, but it is still relevant. Now, any motor will attempt to match the torque of the load. So all motors will match, or they will attempt to match, the counter torque of the load. And that's of the mechanical load, right? So that means that as mechanical load increases, the counter torque on the motor increases. So if the counter torque would be essentially the amount of resistance that the motor feels to trying to turn its shaft. Mechanical load is typically referred to in these terms. So mech load is referred to as counter torque. Whereas motor load or motor rotation, the amount of power that goes into it, is referred to as torque. So the way that we then calculate this is in two different methods, depending if you're in North America or Europe. If you're in Canada, unfortunately, we have to learn them both because we live beside the States and it's highly irritating. So we have T is equal to HP, 5252, all over RPM. And then we also have this one over here, which is T equal to P out times 9.55 all over RPM. So what these are showing the difference between is imperial and metric. That's the only difference. Imperial versus metric. So imperial is the one that we are most used to referring to and use in everyday life. So torque, again, T represents torque. Torque is not only a amount of force, but it's also in a direction. And so torque is measured in foot-pounds when we refer to imperial values. Whereas torque in metric, again, force and direction. When we're talking about torque in a metric environment, it's referred to as Newton meters. Newton meters. So this is foot-pounds, and this is Newton meters. $52.52 would be our standard engineered constant. So is 9.55. So this is just a constant value. The horsepower and the power output are the same thing, aren't they? Because on a motor, the shaft of the motor is where the power output is. So you can either refer to that as horsepower, or you can take 746 watts for each horsepower. And that would then give you the total power output in watts. The RPM is simply the speed, right? Revolutions per minute. So you can calculate torque in either one of these methods. It's up to you, and it really doesn't matter which of the two you use. For instance, if we had a 10 horsepower motor and it operates at 240 volts and it has 2000, it's turning at 2000 RPM. Well, we could calculate both the imperial and the metric torque. So let's do imperial and metric. So imperial would be the horsepower, 10 times 52 divided by the RPM of 2000. So 10 times 52 equals, divided by 2000, 26.26 foot-pounds worth of torque. If we were to do the metric calculation for this, it would simply be, well, 10 horsepower times 746. So that would be 7460 watts, right? Times 9.55, all divided by the RPM 2000. So same idea, 7460 times 9.55 equals, divided by 2000, 35.62 Newton meters. So calculating torque is a pretty straightforward process. You don't have to memorize these equations because they are provided on your equation sheet, and you can refer to those throughout exams and assignments and handouts. So keep these items in the back of your head as you're going through the calculations. Hopefully you have some good success with them.